Welcome to our class. Today we are going to discuss about fundamentals of stress and strain, which is very essential for our engineering works. So let's see one after the other. We are going to start with the stress. When any external force acts on a body, the body tends to undergo some deformation. The resistance by which a body opposes to the deformation is known as strength of material. As the term strength of material, which is the term for our module, which is strength of material. So we want to know the role of stress and strain. But to start with, we are going to see the role of stress on a material. Within a certain limit, the resistance offered by a material is proportional to the deformation brought out on the material by external force. A material, once is subjected to external force, tends to undergo deformation. Those atoms that are within the element or the object tend to undergo deformation because of the external force. But beyond the elastic stage, because each body have a certain property of elastic. So the resistance offered by a material is less than applied force. In such case, the deformation continues until failure takes place. When the force of resistance offered by the body is less than the external force, the deformation continues until the failure takes place. We'll see what is failure of the object when the body exceeds the resistance offered by the body. But within elastic stage, the resisting force equals the applied load. So we'll see what is elastic stage. I've seen this. If this is for stress, let's see on how the relation between the force and extension. So elastic stage is where the body experiences proportionality between the force exerted or applied to the extension of the body. So within this limit, limit is what we call elastic stage. If the force exceeds, it tends to change, or is where we call it will undergo failure. So we'll see where the body will tend to indicate the failure. See? So for the case of stress, every material is elastic in nature, as I said earlier. When some external system of a force acts on a body, it undergoes some deformation. That means we are talking about the atoms that make up the element or the body. So the force of the resistance per unit area offered by a body against deformation is known as stress. It is denoted by a Greek letter, sigma. So the external force acting on the body is called load or force. Note that the load is applied to the body while the stress is induced in the material of the body. A load member remains in equilibrium when the resistance offered by the member against the deformation and the applied load are equal. So mathematically, stress can be obtained by the force applied to the area, cross-section area of the material. So it's where sigma is for stress, called the intensity of stress, and P is for external force or load, and A is for cross-section area. And the units for our stress depends upon the unit of the load or the force that we applied and the unit of the area. In SI units, force is expressed in newtons, written capital N, and area is expressed in meter square. Hence, the unit of stress becomes Newton per meter squared or Pascal. The area is also expressed in millimeter square. The unity of the stress becomes Newton per meter squared. So here we can see on how to present the unit. For the larger quantities are presented by kilogram, omega, giga, tetra, and these stand for the ones that I've talked about, this kilo, mega, kilo, mega, giga, and tetra. They stand for, this kilo means that 10 power 3, mega, that means 10 power 6, represented by capital M, kilo represented by small k, giga is 10 power 9, and this is represented by G. Tera, that is 10 power 12, and is represented by capital T, whereby for smaller quantities are represented by mil, micro, nana, pica. These are, they are equal to the, if you express mil, that means 10 power negative 3, which is represented normally by small m. And micro is 10 power negative 6, which is represented by micro. And nona is 10 power 9, pica is 10 power negative 12, and is represented by p, small p. One can say, what is the thing? If one has 1 ohm, and this one is given to be 1 ohm micro ohm, it means that you are referring to this 1 micro ohm should be divided by 1 million, or should be multiplied by 10 power negative 6. If there is 1 micro ohm, it means you have to divide this 1 by 1 million. Or if you have 6 maybe ohms, that means times, if it is 6 mega ohms, that means you have to take this 6 times 10 power 6, that is for mega. Capital M is for mega. That means you have to multiply the quantity you have by 10 power 6. Okay. So let's see what is strain. We have seen the case of stress for a material. That means once the body has been subjected to load, it tends to deform its structure. That means deformation occurs to the structure of the material, that is, refers to the atoms or molecules that are forming the element or the body. Let's now to see what is strain. Strain, when a body is subjected to some external force, there is some change of dimension. So this makes the difference of stress and strain. For the first part, we have seen that stress undergoes deformation once it's subjected to external force. Here, the body will be subjected to external force as well, but it is going to indicate the change in dimension. That means in the size of the body, so that is strain. The ratio of the change of dimension of the body to the original dimension is known as strain, because we are going to indicate to have the ratio. The ratio, that means the changed object over the original size of the object is going to give us the ratio. So that ratio is what we term it as strain. So let's now see, okay, strain is also dimensionless, because if, let's say, if we take L, for our case, if we take L is our length of the object. L is our length of the object. After being subjected to a certain force, if it is tension maybe, it will extend, it will have an increase of length. So this increase in length, so we call it that the length will have extension because of the force that will be applied. We will see different forces that will be subjected to objects. So if we take the changed length to original length, we get the so-called strain. So here, strain may be tensile, compressive, volumetric, and shear. So we have seen there are 4 categories of strain. That means the body will change with regard to the force applied to it. If the force is pulling the object, it will be tensile. If it is compressing and there is a decrease in length, that is compressive strain. For volumetric, that means the volume of the object tends to increase or to decrease, that is volumetric strain. But here, for shear, the force will be acting tangentially to the direction of force of the object. We will see one after the other. If there is some increase in the length of a body due to external force, then the ratio of the increase of the length to original length of the body is known as tensile strain. And when there is some decrease in length of the body due to external force, the ratio of the decrease of the length to the original length of the body is termed as compressive strain. The ratio of change of volume of a body to the original one is known as volumetric strain. And the last one, the strain produced by shear stress is known as strain. We will see what is shear stress. As I said in the beginning, that the shear refers to how a force is subjected to the load, that is, will be tangential to the force. Okay, types of stresses. So stresses as well can be of two categories, that is normal stress or shear stress. Let's see what is normal stress. Normal stress is the one acting in a direction perpendicular to the area. It is represented by a letter sigma. Normal stress is further divided into, the normal stress also is divided into tensile stress, compressive stress, so let's see this tensile stress. As I have said, the stress induced in the body when it's subjected to, of which is there is an increase in length, is known as tensile stress. This is the body here and is subjected to the force P in both directions. So if this force is pulling away, this object tends to increase in length. So if you take the increased length to the original length, you will get the so-called strain. So the tensile stress acts normal to the area. Consider the figure below. Let's see the figure below. So tensile stress, that means the resisting force or tensile load to the area. You can see our formula, that is P over area is equal to stress. So you can say the force that is the resisting, that is the force offered by the body, or the tensile load, the force that is acting on it. So for the same object, once it's subjected to external force, so this is how, if there is deformation, we get stress. If there is a change in size or dimensions, we get strain. So increase in length, change in length over original length, you get strain. So that has been the tensile stress. For compressive stress as well, for the first part, we saw that the force we are pulling away, but this one is pushing. So the stress induced in a body when subjected result of which there is a decrease in length is termed as compressive stress. Likewise, there will be area and the force applied to it. See the figure for the formula. So for more explanation how this force, this compressive stress can be elaborated, as a result of the compressive stress, the cross-sectional area of the body gets increased since the volume of the body remains constant. Therefore, the decrease in the length will automatically increase the cross-sectional area of the body. As you can see, the forces for both ends are pushing towards the center. So of course, this area, the area here, will tend to increase the cross-section area because this material of the body will be squeezed, will be pushed toward this center. So automatically this, we can see that there is increase in size at the middle, that is compressive stress. As we have said, for the case of stress, we are talking or we are referring to deformation. Deformation of the material. So the formula for compressive stress, as you can see, that is the resisting force, that is internal force, or the pulling or pushing force, P. Likewise for the tensile stress, so cross-sectional area with the capital A, and compressive strain will be the decrease in length, change in length over original length. We can determine the strain. So let's see how shear stress happens. The stress induced in a body when subjected to two equal and opposite forces which are acting tangentially to the body. Here it's very important to note tangential. Tangential across the resisting section as a result of which the body tends to shear across the section. It's known as shear stress. So the shear stress is the stress which acts tangential. As we have said, tangential to the area, that means it's making 90 degrees to the area. Let's see here. This is the force that we are referring to. This force P is pushing formally the rivet. This is the rivet. The rivet formally was in this way. If it is subjected to a certain force, P pushing this direction, mind you, is perpendicular, is forming right angle to the area, this area here. So this kind of stress is termed as shear stress if it is forming right angle or 90 degrees to the area of the object being subjected to force. Okay. Now, consider a rectangular block of height h, length L, and width unit. Let the bottom face AB of the block be fixed to the surface as shown in figure A. This is our figure A. Let a force P be applied tangentially along the top face CD of the block. Such a force acting tangentially along a surface is known as a shear force. A shear force. For equilibrium of the block, the surface AB will offer a tangential reaction R equal and opposite to the applied tangential force P. So this is our force P, and this one, the reaction R. That means if there is a force P pulling to the left-hand side, and the reaction will be pulling to the right-hand side. That means opposing or opposite or equal to the applied force. So consider a section XX or parallel to the applied force, which divides the block into two parts. The upper part will be in equilibrium if P is equal to the resistance. Equilibrium will only happen if the two forces, the applied and the resisting, will be equal. That means the body will remain in its state. This is shown in figure B. Similarly, the lower part will be in equilibrium if P is equal to the resistance R, as shown in figure C. This is the resistance known as the shear resistance, and the shear resistance per unit area is known as the shear stress, which is represented by a letter tau. Tau. Shear stress, tau, shear resistance over shear area, R, to capital A. And you can now determine this shear stress by P over shear, that is area, over area, L times 1, where R is equal to P and A is equal to L times 1. This diagram can clearly show what we have been expressing up there. Note that the shear stress is tangential to the area over which it acts. As the bottom face of the block is fixed, mind you, the face ABCD will be distorted to ABCD. As you can see now, the C1 and D1, it indicates or it shows that there is a change in C and a change in D as well through an angle thou as a result of force P as shown in figure D. This is our figure D, and shear strain is given by, so in order to determine the shear strain, transversal displacement over the distance AD. So this is our diagram to elaborate what we are discussing. Formerly we had D and C. After being subjected to tangential force, that is the force that is making right angle, because this object is fixed down there. At this surface, the body is fixed, the body A, B, C, D. If the upper part is subjected to force acting on DC or DC, yes, as you can see the force P. So there is a change. This side has moved to D1, and this C has moved to C1. So there is a change of angle, thou. So it is fixed to the left, to the length L. So this is our formula on how to go in order to determine the shear strain. The shear strain can be determined by the following formula. But here we have only obtained the angle. When an external, okay, this is elasticity and elastic limit of a body that is subjected to external force. Let's see what is elasticity and the elastic limit when occurs for the object. When an external force acts on a body, external force, the body tends to undergo some deformation, as you have said earlier. If the external force is removed and the body comes back to its original shape and size, the body is termed to be elastic one. If it can return to its original shape and size, that body is experiencing elasticity, or is termed to be the elastic body. This property, by virtue of which certain material return back to original position after removal of the external force, is called elasticity. Now the property is known as elasticity. The body will regain its previous shape and size only when the deformation caused by the external force is within a certain limit. This property can exist or can be experienced to a certain force. Thus, there is a limiting value of a force up to, and within which the deformation completely disappears on the removal of the force. I've said every object have got this property of elasticity, but there is a condition or there is a limitation. The value of stress corresponding to this limiting force is termed as elastic limit. The boundary for the force that can be experienced for a body which has been subjected to external force to continue to behave at its original, to behave as formerly, that is to return to its original shape and size, have got a limitation. So if the external force is so large that the stress exceeds the elastic limit, the material loses to some extent its property of elasticity. When the force is removed and the material does not return to its original shape, the size will be a residue deformation in the material. So according to this expert, Hooks, so came out with this law regarding this elasticity. So Hooke's law states that when a material is loaded or subjected to a load within an elastic limit, the stress is proportional to the strain produced by the stress. This means that the ratio of the stress to the corresponding strain is constant within elastic limit. This constant is known as modulus of elasticity or modulus of rigidity or elastic module. So you can see one constant has got three names on how to address it. So this will depend upon the locality or of origin. Some will prefer the modulus of elasticity. Some will tend to refer to modulus of rigidity according to the field, and some will term it elastic module. So one should be aware of the three terms which are focusing one constant. This law is named after Robert Hooke, who first established it by different experiments that were conducted while making tensile tests on a metallic bar. He took enough precautions to ensure that the force is applied actually, and the bending of the bar is prevented. He assumed that during the tension, or the longitudinal fibers of the bar have the same elongation. All the cross sections of the bar, which were originally plane, remain so after the extension. This is how this Robert Hooke conducted the experiment to see how the proportionality between stress and strain remain constant within the elastic limit of any material. Modulus of elasticity, or Young modulus, the ratio of tensile stress or compressive stress to the corresponding strain is a constant. This ratio is termed as Young modulus or modulus of elasticity, and is denoted by a letter or a capital letter E, that is tensile stress to the tensile strain, or compressive stress to the compressive strain. So stress over strain is equal to Young modulus. E is a constant, is equal to a constant of proportionality known as modulus of elasticity or Young's modulus. So after several experiments conducted, these experts have come up with constants for different materials. So here is a few to show you: steel, wrought iron, copper, brass, aluminum, timber. So you can see. So as we said, that modulus of elasticity, it's very important to know this, because you are dealing with the material as engineers or for different construction. You need to know this. To what extent this one will be strong enough to resist the load subjected to it, or if you undergo calculation, the C for timber, the common material that you use, that is steel. So stress The ratio of shear stress to the corresponding shear strain within the elastic limit is known as modulus of rigidity, as I have said, shear modulus. Also, so shear stress to the shear strain, as we saw for the compression or tension stress to the strain. Thank you. So deformation of a body due to force acting on it. Consider a body subjected to a tensile stress. Let P be equal to load or force acting on a body, L, length of the body, A, cross-sectional area of the body, and this stress induced in the body, modulus of elasticity for the material of the body. So E is for strain and the change of length, deformation of the body. So strain, as we have said, refers to the change of size of the body. If you would like to determine the strain, you have to come out with this. You have to consider the following. We know that the stress can be determined by the force applied or resisting force over the cross-section area of the body. So you can get the stress, whereby strain is equal to stress over Young modulus. Over Young modulus can be determined the stress, the strain. And mind you, the deformation is equal to the change of size. That means for our case is length. So if you take the change of length, which is equal to Young modulus multiplied by the original length, or the force applied times the original length over cross-section area times the Young modulus, you determine the deformation. So here, to put in a summary, one can say the above formula holds good for compressive stress also. For most of the structural material, the modulus of elasticity for compression is the same as for tension. Sometimes it is, in calculations, the tensile stress and tensile strain are taken positive, whereas compressive stress and compressive strain is regarded as negative.